Good evening, everyone. I'm Lokesh. Currently, I'm doing MTech in radio frequency and photonics in Department of Electrical Engineering. So today we will be discussing about a course which is Introduction to Photonics. So let's move to the first topic of the course. So before that, let's why we are studying photonics. What is the application of photonics? So, photonics is the science of light. It is the technology of generating, controlling, and detecting light waves and photons, which are particles of light. The characteristic of the waves and photons can be used to explore the universe, cure diseases, and even to solve crimes. Scientists have been studying light for a hundred of years. The color of the rainbow are only a small part of the entire light wave range called the electromagnetic spectrum. Photonics explore a wider variety of wavelengths from gamma rays to radio, including X-rays, UV, and infrared light. So next is application of photonics, where we use uh, photonics, like the concept of photonics. So, like even if we cannot see the entire electromagnetic spectrum, visible and invisible light waves are a part of our everyday life. Photonics is everywhere in consumer electronics, like for example, bars, scanner, DVD player, remote TV control, in telecommunication for internet, in health for eye surgery, medical instrument, in manufacturing industry for laser cutting and machine, in defense and security for infrared cameras and remote sensing, and in entertainment, like for example holography and laser show and so on. Now next move to the content of the our course. So, like these are the content of the course, like starting from ray optics, wave optics, electromagnetic optics, and quantum optics. So, these are basically like a subset. Like ray optics is a subset of wave optics is a subset of electromagnetic optics, electromagnetic is a subset of quantum optics. And like in electro quantum optics is actually contain the whole this much of syllabus. And now in 21st century, we are using quantum optics. With this content, we have one more, that is nonlinear optics. So let's move to our first topic, that is ray optics. Ray optics, which is also called a fiber optics. So Sir Isaac Newton and D. Fermat, through experimentally, they have proposed that the light travels in a straight line. So the behavior of light can be adequately described by rays obeying a set of geometrical rules. This model of light is called ray optics. In ray optics, the dimension of object is much larger than the wavelength of the light. Like d is far much greater than lambda. I mean, the dimension of object through which the light is passing has to be much greater than the wavelength of the light. So next is, then only we can say that it is a ray optics. Now let's move to the next one, that is raw reflection or Snell's law. So like everybody knows about this Snell's law. It's like a Snell's law states rays in two, like a refracted rays and a refracted rays. So it's basically like we have one boundary above which we have air with a refractive index of n1, and below we have some glass or some water with a refractive index of n2. So when the incident light falls on the this boundary with some theta 1 with a normal to the boundary, it will have reflected ray and the refracted ray. Reflected ray and the refracted ray. So this the theta 2, which is the refracted angle, is basically depend on the theta 1, which is the incident angle. So basically, with the formula like Snell's law, we know that n1 sin theta 1 is equal to n2 sin theta 2. So this theta 2 is actually dependent on the uh, uh, incident angle, and the reflected angle is actually basically equal to the incident angle only. So next, move to the simple optical components. So, first component is planar mirror. So, planar mirror is like a planar mirror reflects the rays originated from a point P, such that the reflected ray appear to originated from a point behind the mirror, called the image. So, basically, what does it mean? Like, uh, suppose like we have a mirror with a silver coating or a highly polished metallic surface. So if we have some object over if you have some object over here, then and we are observing from somewhere here, like maybe we are from observing some from here, we have like we are from observing here. So like from this side, we will, if we saw in the mirror, we will see we will see the mirror here, somewhere here. So what does means like behind the mirror means like when we see from this, we will see this kind of mirror with this kind of image in the mirror, and the distance from mirror to the real image and mirror to the imaginary image will have a same distance. So that is what it does means. Like it means like the surface, like the planar mirror reflects rays originating from a point P, such that the reflected rays appear to originated from a point behind the mirror. So this is actually called the mirror. Now again, the next is paraboloid mirror. So, we have to explain the for the examples of some mirrors is like general we use in our household mirror. So next move to the paraboloid mirror. Paraboloid mirror is like the surface of paraboloid mirror is like it is useful property of focusing all the incident rays parallel to its axis parallel to its axis to a single point called the focus. So basically, what does it mean? Like, so next is paraboloid mirror. So paraboloid mirror means like the surface of this mirror is like it has a useful property of focusing all the incident ray parallel to its axis to a single point, and that point is called a focus. So like, what does it mean? Like we have some paraboloid mirror, and this is the axis. So the light which are parallel to the axis. gets focused at a single point, which we call as a focus point. So the light, which so this is actually the axis. This is a paraboloid mirror. So the light which are parallel to this axis, like gets like focus at a single point. So that is what it means. Uh, the surface, like it has a useful property of focusing all the incident rays parallel to its axis to a single point. So where do we like what is its significance and what is its importance? So it is used in light collecting elements in a telescope. So for example, uh, so like in telescope, there is an antenna, like actually not antennas, kind of something we usually see. And there is something like a notch kind of here. So like the waves, the rays which are actually parallel to this axis gets focus at this point. So that's how we use in a telescope. And there is another views. It's like a flashlight. So the flash, I mean the headlights, the car's headlights. So where the there we also use the paraboloid mirror. So in paraboloid mirrors, basically this is the focus. At the focus point, we have a light, and actually it reflects the light in every direction like this. It reflects light in all direction, and from this, the light reflected back parallel to the axis. So that's how we. So that is what happens in the headlight of the light, like headlight of the car. Now, next is elliptical mirror. So, uh, like uh, so, an elliptical mirror. So, what is elliptical mirror? So, an elliptical mirror reflect all the rays emitted from one of its foci and image into onto the other foci. So, again, what does it mean? Like we have the elliptical mirror. It's a kind of elliptical mirror where we have one foci over here and one foci over here. So when the light scatter from this point in all direction, so when light scatter from this in all direction, after reflecting from the surface of the elliptical mirror, it gets focused to another foci. So this is basically foci one and foci two. So like all the mirror get reflected back to the another second foci. And where we use this, it's like a example, like a bathroom mirror. It's a fine, for well, like it don't have doesn't have a much of importance in a real life. It uses in bathroom mirror or some decorative wall mirror. So and also sometimes it's like a use in a incident the light of lamp into optical fiber or light guide. I mean, we have a light over here, light source here, and we have to keep the fiber over here. So the all the light which are scattering from here will get reflect to the fiber elements. So these are some uses of the elliptical mirror. The now next is spherical mirror. So spherical mirror, it has neither the focusing property of the paraboid mirror nor the imaging property of the elliptical mirror. So, again, with the if we draw the diagram, like it's easy to draw like to made a spherical mirror. So, like this is the axis. This is the axis. The rays which are actually parallel to this don't get focus at a single at a focal point. So this is suppose the focal point. So this is suppose like a focal point. So the lines basically don't reflected back to the focal. It's some it reflect back to some arbitrary angle like this. But one more thing is like the rays, the rays which are very close to the axis, like this, like this. Those rays actually get, I mean, they reflected back to a single point. So, like this is suppose our focus. So the light which are reflected gets focus at a focal point. So basically, but the rays has to be very near to and parallel to the axis and also very near to the axis. So then only it can get focused to a single point, focus point. So where do we use this mirror? So basically it has a use in as a concave mirror or a convex mirror. Concave mirror generally we see is in dental we have in dental mirror we they use generally use the concave mirror in like for convex mirror usually we saw this convex mirror in parking area. Now next move to the next topic, that is basic of fiber optics. An optical fiber is a cylindrical waveguide made up of low loss materials such as silica glass. It has a central core in which the light is guided, embedded in an outer cladding of slightly lower refractive index. So this is the fiber optics where we have core, the inside the in inner part is core and this outer part is called as the cladding, where the refractive index of this core is N1 and the refractive index of cladding is N2. So like here you can see that core, this is core, and this is cladding, and we have one more outer cover which we call it as a jacket. This core has been made by uh, the material silicon dioxide plus germanium dioxide. So adding germanium dioxide will make the core refractive index to be higher than the cladding. And so the light rays incident on the core cladding boundary at angles greater than the critical angle undergo total internal reflection and are guided through the core without reflection into the cladding. So we if the refractive index of core is greater than cladding, we will have a total internal reflection like this. Again, it depends upon also the incident angle also. So if the incident angle is greater than critical angle, there will be a total internal reflection like this. But if it is not, if it is less than critical angle, then there will be a loss in cladding also. Next is numerical aperture. Here, like numerical aperture came from the acceptor angle. So let's define the acceptor angle. So acceptor angles is the maximum angle of a ray, like maximum angle of a ray hitting the fiber core, which allows the incident light to be guided by the core. The incident light to be guided by the core. The sign of that uh, angle, that acceptor angle, is called the numerical aperture, and this it is essentially determined by the refractive index of core and cladding of the fiber. So, like here we have the acceptance cone, and this is the acceptance angle. The light rays which are going through this cone will have a total internal reflection. So there won't be any loss in the fiber cladding, but the rays which are the angles which have a greater than the accepting angles will go into a refraction and also reflection. So there will be a loss in cladding also. So like here you can see that we have a perfect reflector where there won't be any loss, but there won't be any loss, and here we will have a total internal reflection. But here in air class medium, there will be a reflection and there will be a refraction. So for incident angles less than critical angle, there will be a loss. Like you can see here the graph. And but for theta I, the incidence angle greater than the critical angle, there will be a total internal reflection. There won't be any loss. So like here for like you can see here, there will be a loss in cladding, and there is also a reflection back also. So the numerical aperture is basically the sign of the acceptor angle. The numerical aperture therefore describes the light gathering capacity of the fiber. Light rays within the accepting cones are guided by the total internal reflection. Now, next is attenuation coefficient of fiber optic. So this is the graph of attenuation of silica glass versus the wavelength. So for the smaller wavelength, we will have a Rayleigh scattering. For this much of the wavelength, we will have a OH absorption, and for the larger wavelength, we will have infrared absorption. So here we have absolute minima and local minima. This absolute minima comes around some 1.55 micrometer, which is actually 1550 nanometer. So this wavelength mostly used in optical communication because it has a loss of some 0.15 dB per kilometer, which is uh, too low. So we can use this for the longer communication. And here we also have one local minimap, which comes at something 1.3 micrometer, like 1300 nanometer. So this local minima also have some loss of 0.3 dB per kilometer. So these two things can be used. These two wavelengths can be used for the longer transmission, but generally 1550 nanometer, that 1.55 micrometer, is used for the optical communication. The and like attenuation coefficient of silica glass versus the wavelength. So this is the attenuation coefficient of silica glass versus the wavelength. There is a local minima at 1.3 micrometer, which has a loss of some 0.3 dB per kilometer. This is the local minima of at 1.3 micrometer, and we have an absolute minima at 1.55 micrometer, which is basically used, which have a least loss, that is 0.15 dB per kilometer. So this is basically used for the optical communication. So because of this low loss, optical fibers long ago replaced copper cables for data communication. Next is optical waveguide. The underlying principle of optical confinement is simple. A medium of refractive index N1 embedded in a medium of lower refractive index N2, which is less than N1, act as a light trap within the optical rays, remains confined by multiple total internal reflection at the boundaries. So these are two dielectrics with having a different refractive index. So like the way we have seen here, like a core have the more refractive index compared to the cladding. So this will make sure that there will be a total internal reflection. The same things happens or in this also. This has a more refractive index compared to the outer surface, and because of that, there will be a total internal reflection. So there we have some kind of dielectric waveguide, like we have a slab, we have steel, and this is fiber. This is basically looks like this optical fiber, but it is actually the dielectric waveguide surrounded by the another dielectric waveguide. The most advanced technology of fabricating waveguides is titanium, lithium nanobit. This is basically titanium, lithium nanobit. So we are the titan. This is basically will have a titanium, and the surrounded will it will be surrounded by the lithium nanobit. An embedded strip waveguide is fabricated by diffusing titanium into a lithium nanobit substrate to increase its refractive index in the region of the strip. So it will have a higher refractive index compared to the outer surface, which will make it to the total internal reflection. Now, again, we can use also gallium arsenide strip waveguides are made by using layers of gallium arsenide and aluminum gallium arsenide of lower reflectivity. Another semiconductor material that has recently gained importance in waveguide is indium phosphide. So basically nowadays, like we can see, uh, like everybody is using indium phosphide for the as a waveguide. Next is types of waveguide. So first one is planar mirror waveguide. Light propagating waveguide compromising two parallel infinite planar mirrors separated by a distance d. The mirrors are assumed to reflect light without loss. So these are the mirror which actually reflect light without loss, without any loss. There will be a two mirror, and we will have a total internal reflection inside here. So, but like it is not used in practical application because of the difficulty and cost of fabricating low loss mirror. The next is planar dielectric waveguide. Uh, Planar dielectric waveguide is a slab of dielectric material surrounded by a media of lower refractive index. The light is guided inside the slab by total internal reflection. Here we have used a mirror which without loss, but here we have like two dielectric material, like the N1 have a one they are different dielectric, and N2 is a different dielectric. The dielectric this dielectric has to be more refractive, like should have more refractive index compared to the this outer dielectric surface. We have some kind of strip or a figure of dielectric waveguide, like we have embedded strip, then we have strip, a ridge, and strip loaded. Next is different configuration of waveguide. So like we have a different kinds of like we can different configuration of waveguides. Like you can see there is a straight, there is a like this is like a S bend, this is Y branch, this is a Maxander, this is basically a two Y, uh, then this is one Y and this is another Y. Then we have a directional coupler. Then we have a intersection uh, coupler, intersection waveguide. So basically, this is a directional coupler mostly used in the chips, mostly used in chips. So like, let's see where we do use this waveguide. So S bends. So these S bends are used to offset the propagation axis. So basically, it like if the light is propagating in this axis, like the this S will bend to offset the propagation axis. Then we have the wire branch plays the role of beam splitter or combiner. So like if the light has been propagated, the light has been propagated to this, there will be a beams. It acts as a beam splitter. If the beams are coming from this, it will act as a combiner also. Then we have two wire branches may be used as a to make a Mach-Zehnder interferometer. So this is actually a Mach-Zehnder interferometer. Like this is used in a Mach-Zehnder interferometer. Two waveguides in close proximity or interacting can exchange the power and may be used as a directional coupler. So, like this is the directional coupler where, like I have said, that it is mostly used in the microchip where there can be interacting and can exchange of the power. Now, next is input coupler. So, coupling plays an important role of focusing the LED or laser source on waveguide, which gives maximum output at the other end of waveguide. The amount of light can be accessed by using array optics approach. For maximum coupling efficiency, the incident line should be focused within the angle theta. Again, the light may be coupled into a waveguide by directly focusing it at one end. But because of the small dimension of the waveguide's light, like the dimension of the waveguide is very small, because of that, the focusing and alignment are usually difficult, and coupling using this method is inefficient. So we have for this for light to be coupled, we have this kind of methods that we have used. So there are four techniques for coupling light to the optical fiber. So we have a prism coupling. This is a grating coupling. Then we have a butt coupling, and this is chain coupling. So if we combine these two, this C and D, then we will have some chain butt coupling also. The next is fiber V parameter. The normalized frequency parameter of a fiber is also called the V number. It is useful specification. Many fiber parameters can be expressed in terms of V, such as the number of mode at given wavelength, mode cutoff condition, and propagation constant. So this is V. This is the actually the V. This is the formula for V wave number is equal to 2 pi into A upon lambda into Na, where A is the diameter of the fiber, and sorry, not a fiber, actually it is the radius of a fiber, and this is the wavelength, and this is the numerical aperture. So for B to be less than 2.405, we can see the single mode, and for B greater than the 2.40, we will have multi-mode. So basically, we actually define that the fiber, the waveguide or the fiber will be a single mode or a multi-mode. So like if you can draw like here, if we have draw, like it can intersect to one mode. So like it has, so that's why it is a single mode. Here, like here it intersects two modes. So the fiber is actually the multi-mode. Here if we actually, if you draw the line like that, it will intersect six modes. So the B is equal to 10 will have six modes of uh, six will have the that fiber will have a six mode. So basically, like by changing the lambda value, like if we increase the lambda value, the we the like the mode will change to a single mode. If we decrease the lambda value, the modes will go to the multi-mode. So it is directly proportional. So this V number is directly proportional to the radius to wavelength ratio, that is A by lambda naught, and the numerical aperture. Next is wave optics. Christian Huygens and Thomas Young, from experimentally, they have proposed that light travels as a wave. The wave optics theory to be useful when the light rays propagate through and around objects whose dimensions are very close to the wavelength. So for ray optics, we have seen that the dimension of the object is far much greater than the wavelength of light. But in wave optics, the dimension is almost equal to the wavelength of the light. It is possible to describe many optical phenomena such as diffraction and interference using simplified scalar wave theory. So basically, this is the experiment of wave optics, where the slit width that this slit width is actually comparable to the wavelength of the light. So when light falls on this object, the light gets bends, and we have constructive and destructive interference. So, like, suppose this is a scale, we will have some constructive and destructive interference on the both sides, like this. So this is constructive, this is destructive, this is constructive, this is destructive. Now, next is optical frequencies and wavelength. As the wavelength increases, the rays have been divided into the different regions. So, like as you can see that as the wavelength is increases, the rays have been divided into different regions. Like for a very small wavelength, like it has been divided like gamma rays, X rays, ultraviolet rays, visible rays, infrared rays, microwaves, and radio waves. So, and each rays and waves have its own application. Like for gamma rays, it is used in PET scan. Like X-ray, it is in airport security scanner. Ultraviolet is basically the UV light which comes from the sun and visible. Like we know, like it's visible. Like its wavelength ranges from some 390 nanometer to 760 nanometer. Then we have infrared, which is used in night vision goggles, some TV remote control. And we have then a microwave. Like we all know about the microwave oven, and also it is used in the aircraft communication. Then we have a radio waves, which are uh, AM, like amplitude modulation radios. Generally, the old radios used to operate at this wavelength. So the range of the optical wavelengths contains three regions: infrared, visible, and ultraviolet. So basically, the optical contains uh, infrared, this visible range, and this ultraviolet. In frequency, optical waves lies in the range of 3 into 10 power 11 to 3 into 10 power 16 hertz. Next is diffraction, diffraction of light. Diffraction is the bending of waves around obstacle or change in the direction and intensity of group of waves after passing by an obstacle or through an aperture whose size is comparable to the wavelength of the waves. So this lead with this distance has to be equal to the wavelength of the light. Then only we will have a constructive and destructive interference. So like if we do this experiment in a lab, like this kind of things like we will see in the lab. Like this is for the this will you will get this for the single slit experiment. This is for double slit experiment, and this is a circular slit. So like this is actually basically maxima. This is minima. The darker part is maxima. The this black is minima. Then again maxima. Then minima. Again we have this maxima. Here we have minima, maxima, minima, maximum, and this is actually a minima. Again in circular, this is central is maxima. Then we have minima, maxima, minima, like that. Next is interferometer. An interferometer is an optical instrument that splits a wave in two waves using beam splitter, delays them by unequal distance, redirect them using mirrors, recombine them using another beam splitter, and detects the intensity of their superposition. So there are three important for interferometer as follows: Michelson interferometer, Alexander interferometer, and Sagnac interferometer. So first is Michelson interferometer. So Michelson interferometer is like is the produces interference fringes by splitting a beam of light so that one beam strike a fixed mirror and other beam a movable mirror. Then the reflect beams are brought back together and interference pattern result. So like this is a beam, this is a laser, this is a beam splitter. There is a fixed mirror, and suppose this is a fixed mirror and this is a movable mirror. So with this, we will have a like fringe pattern like this. We will get a circular fringes pattern on the screen. So this is useful. Microsoft interface is useful to find the wavelength of the laser. Like by moving the movable mirror, we can find the interferences, and like we can calculate from there the wavelength of the light. Then next is Alexander interferometer. Mach-Zehnder interferometer is an optical instrument that splits a wave in two waves using a beam splitter, delays them by unequal distance, redirect them using mirror, recombine them using another beam splitter, and detect the intensity of their superposition. So basically, we have one beam splitter over here, one second beam splitter over here, and there is a two mirror over there. So, like when light falls on one first beam splitter, it gets two like it pass through the one mirror, and the another it get passed to the another mirror, and then again they recombine to another beam splitter where we have two screens where like we can find the fringes. So what is the use of this like Mach-Zehnder interferometer? So example in the thermo-optic switches. It's like thermo-optic switches in like in electronic gadgets. Like what is thermo-optics? So basically, thermo-optic switches are generally based on the thermo-optic effect, which is change of the refractive index caused by the temperature variation of the material. Next is Sagnac interferometer. So, Sagnac interferometer is an optical instrument that splits a wave into two waves using beam splitter, delays them by unequal distance, redirects them using mirror, recombine them using same beam splitter, and detect the intensity of their superposition. So, in a Sagnac interferometer, we have one beam splitter and three mirrors, and here we have a screen. So, what is the use of Sagnac interferometer? So, it has a very wide use in our day-to-day life. So, for example, it is used as a gyroscope. So, gyroscopes are the core of today's inertial navigation guidance and control system for aircraft, missile ships, and land vehicles. So, like even like if you see the ships, even though if there are waves coming in the water, the ships don't like it don't shift it will be stable in their position. This is because of the gyroscope. Next is electromagnetic optics. So James Clerk Maxwell. So we all like we know that all the electromagnetics like it's based on the Maxwell equation only. So like James Clerk Maxwell have through experimental he has proposed that the light travels as electromagnetic waves. The electromagnetic optics produce a vector nature of light comprising the electric field and magnetic field that vary in time and space. So basically, wave optics is approximation of electromagnetic optics that relies on the wave function, a scalar function of time and space. So we have this four equation of Maxwell equation, and this is the like electromagnetic wave. So we have one. This is uh, electric field like in upward direction, and we have this is magnetic. So and its propagation is propagating in this direction. So basically, electric field, magnetic field, and the propagation direction they all has to be perpendicular to each other. So we have the four equation here, Maxwell equation that is del cross C is equal to rho v by epsilon, del dot H is equal to 0, del cross C is equal to minus mu dou H by dou T. That is, this is Gauss law. This is the Gauss law of magnetism. This is actually Faraday's law. And like del cross H plus J plus epsilon or dou E by dou T. This is Ampere's law. This is actually modified Ampere law. So basically, Ampere's law is just has just only del cross H is equal to J. But in modified Ampere's law, we have one more term that is epsilon dou E by dou T. Next is polarization of light. The generalized equation of electric field is like for example, this is the generalized equation of electric field like AX cap plus EX plus AY cap EY e power j phi into e power minus j kz. So basically, this phi will decide the polarization of the electric field. So let's see what with what if phi is zero, what kind of polarization we will get. So for phi is equal to 0 or pi, we will have a linear polarization. So like for if phi is equal to 0 and pi, there won't it will have a real value. So it will be a linear polarization. For phi is equal to plus or minus pi by 2, and this magnitude Ex and Ey, if they are equal, then we will have a circular polarization. Again, for phi is equal to plus or minus pi by 2, and if this magnitude Ex and Ey magnitude is not equal, we will have elliptical polarization. Next is linear polarization. So like as you can see here, if it is a light source and we have some electromagnetic, we have some horizontal and vertical magnetic waves, like electromagnetic waves. So and this is a linear polarization. Basically, this polarization will detect like which kind of polarization that can pass through it. So like it is a vertical polarized, so the waves which are vertical that only can pass through it. So the figure, the lines in the polarizer represent the field direction that is permitted to pass. So that is what I have said. Like the lines in the polarizer, these lines. So these lines will represent the field direction that is permitted to pass. We have again a matrix. Like this is actually a matrix representation of polarization device. So for this, like for polarization of light, Jones matrix, this has to be like we have this Jones matrix for linear polarization. The matrix has to be 1001, the Jones matrix. For the circular polarization, or if there is a shift of pi by 2, then this Jones matrix will be different than this one. Next is wave retarder. Wave retarder is an optical device that alters the polarization state of light wave traveling through it. So this is actually a wave retarder. So basically, it will give a shift of some pi by 2 or pi. So and accordingly, we will get the polarization on the screen. So basically, if we have a linear polarization in x and y direction, and wave retard is having a shift of pi by 2 in one direction, so then we will get circular polarization. Same for if we have a circular polarization, there will be a shift of pi by 2 in some one direction, and we will get a linear polarization. Again, here the shift is pi. For linear polarization, if there is a shift of pi, the direction will be changed, but the polarization will be same. So if we have this kind, if we have this linear polarization, then there will be a shift of 180 degree here. Similarly, if you have circular polarization, then for the shift of pi, we will get the same polarization but in a different direction. So basically, this is the quarter wave retarded, and this is the half wave retarded. So the amount of light reflected at the boundary between two materials depends on the polarization of incident wave. The amount of light observed by certain material is a polarization dependent. Light scattering from matter is generally polarized sensitive, used in sunglasses to cut off unwanted reflected light. So basically, so like when we travel or drive a car at night, so we can't see like this is the image that we usually see. Like we can't see the what like what is coming from front. So like using these sunglasses, which actually polarize the light, like we can see like this is the what we can see from the sunglasses. So like it will clear the image and like it will be useful like for the driving also. The next is reflection and refraction. So we have dielectric material N1 and N2. This is incident wave. It has some reflected wave and a refracted wave with some theta, angle theta 2, and this is actually a plane of incident. So transfer field and transfer magnetic field polarization. The X polarized mode is called the transfer polarization or the orthogonal polarization. Since the electric field are orthogonal to the plane of incident. So this is the plane of incident and electric field is in upward direction which is perpendicular to the plane of incident. So that's why it's called the transfer electric field. The Y polarized mode is called a transfer magnetic polarization since the magnetic field is orthogonal to the propagation of light, or the parallel polarization since the electric fields are parallel to the plane of incident. So this is actually why where the magnetic field will be there and it is actually perpendicular the incident wave. So that's why it's called the transfer magnetic field. The orthogonal and parallel polarization are also called S and P polarization respectively. So P polarized means parallel to plane and S polarized means perpendicular to the plane. So applying the boundary condition that is equating the tangential components of electric field and tangential component of magnetic field at both sides of the boundary, like by applying the boundary condition. In each of the transfer electric and transfer magnetic cases, we obtain the following expression for the for the reflection and transmission coefficient. So this is basically the reflection coefficient in x direction, and this is the reflection coefficient in y direction. This is transition coefficient in x and transmission coefficient in y. So this is basically for TE polarization, and this is TM polarization. And with this equation, we can get the electric field in this dielectric, the reflected field in this direction, like a reflected electric field, refracted electric field, reflected magnetic field, or refracted magnetic field. So with this equation, we can find everything. So like this equation for a reflected wave and these equations are for transmitted wave. Now, next move to the another topic that is quantum optics. So, Max Planck and Albert Einstein, so they have differently proposed that for Max Planck, he has proposed that light emission and absorption is contains, where Albert Einstein says that light compromise of quantum energy, which is basically photons. Optics provide the most complete treatment of light within the confines of classical optics. Although electromagnetic theory is capable of providing explanation for a great many effects in optics, but fails to account for certain optic phenomena such as absorption, emission, and photoelectric effect. Basically, through photoelectric effect, Albert Einstein have proposed that light compromises of quantum energy. Like we have, like this is the quantum. This is the final part of our topic. We have one more, that is nonlinear optics also. Quantum electromagnetic theory is or quantum electrodynamics, that is QED, or quantum optics is today accepted as a theory that is useful for explaining almost all known optical phenomena. The next move to photon properties. What is photon? From quantum perspective, light consists of particles called photon. Photon carries electromagnetic energy and momentum as well as intrinsic angular momentum associated with its polarization properties. It can also carry orbital angular momentum. The photon has zero rest mass and travels at the speed of light in vacuum, that is C naught. C naught is the speed of light in vacuum, and its speed in matter is reduces to C, which is less than the speed of light in vacuum, which is C naught. The notion of photon initially grew out of an attempt by Max Planck in 1900 to resolve a long-standing riddle concerning the spectrum of black body radiation. And again in 1905, Albert Einstein extended the notion of quantization by considering the light itself to be a collection of photons. This enables him to successfully explain the photoelectric effect. So basically, this is the photoelectric effect that is experimentally done by the Albert Einstein. So like we have a detector here, we have a metal surface here. So when light falls on the metal, like the electron gets charged and it moves to the positive terminal of the uh, positive terminals, and so there will be a current. So because of that, there will be a current that is flowing through it. Next is photon energy. Optics provides that the energy of an electromagnetic mode is quantized to discrete levels separated by the energy of photon. The energy of photon in mode of frequency mu is equal to E is equal to h mu, where mu is equal to c by lambda or lambda is equal to c by mu. Photon energy is thus E is equal to h mu. So like if you put the mu is equal to c by lambda, then we will have like h into c. This whole value is equal to 1.24 electron volt. So this is the same as the kinetic energy imparted to electron when it accelerated through a potential difference of 1.24 volt. The conversion formula between wavelength and photon energy is therefore, so this is the like E is equal to h mu if we put lambda, like mu is equal to c by lambda. So this h into c, we will have a 1.24 electron volt and we will have a lambda. So basically electron energy in electron volt is equal to 1.24 divided by a wavelength of a photon in micrometer. If the wavelength is in nanometer, then we will have here like energy in electron volt is equal to 1240 divided by lambda naught in nanometer. Next, interaction of photon with matter. Um, and here we will see the interaction of photon with atom. As is known from atomic theory, an atom may emit or absorb photon by undergoing downward or upward transition between its energy levels, conserving energy in the process. The laws that govern this process are described in quantum optics. So basically, when this is some atoms, and when the light, like incoming photon hits one electron, it gets it gets energized and it move to the higher state. We are particularly interested in the interaction between the atom and the photons of this sky. Radiation mode of frequency where h mu naught is equal to E2 minus E1, where basically E2 will be the higher state and E1 will be a ground state. Since photon of this energy match the atomic energy level difference, the photon energy has to be equal to E2 minus E1. Such interaction are formally studied by the use of quantum optics. three forms of interaction are possible. So we have three forms of interaction like absorption, spontaneous emission, and stimulation, stimulated emission. So we will discuss one by one. So first is absorption. If the electron in an atom is initially in the lower energy level and the radiation mode contains a photon, the photon may be absorbed and the electron in an atom raised to the upper energy level. This process, which is induced by the photon, is called absorption. It can occur only when the mode contains a photon. So basically, if we have the electron at the ground state, so the photon with the energy, which is has to be the energy has to be equal to the E2 minus even the energy difference between those two. If the photon has this much of energy, then the electron will absorb this energy and it will go to the higher state. Next is spontaneous emission. If the electron in an atom is initially in the upper energy level, it may decay spontaneously to the lower energy level and release its energy in the form of photon. So basically, the electron always wanted to stay in a stable condition. So when the electron at higher state comes to the ground state, uh, it emits the photon which have a energy equal to E2 minus E1 again. So the photon energy H mu is added to the energy of the electromagnetic mode. The process is called spontaneous emission because the transition is dependent on of the number of photons that may already be in the mode. So basically, if we have more like two more photons with the same energy level, then if they all three will come to the ground state, and we will have three photons that will be emitted from here. So this is called the spontaneous emission. The next is stimulated emission. Basically, this is what is used in laser. If the electron in an atom uh, is in the upper energy level and the radiation mode contains a photon, the electron may be induced to emit another photon into the same mode. This process is known as stimulated emission. It is the inverse of the absorption. The presence of photon in a mode of specified frequency, propagation direction, and polarization stimulates the emission of duplicate photon with precisely the same characteristic as the original signal. So, like if we have electron at a high energy level and the photon with the energy with equal to E2 minus E1, if it hits the uh, electrons, then the electron higher energy state will come to a ground state. Plus, it will emit two photons which have the same characteristics, which means it will have the same amplitude, same phase, uh, like, and it has the same characteristic amplitude and phase. It will be similar in all characteristics. This photon amplification process is the phenomena that underlines the operation of laser amplifiers and lasers. Now, next is fluorescence spectroscopy. So, what is fluorescence? Fluorescence is the phenomena that materially emits light at wavelength when you illuminate it at another. Fluorescence method is called a fluorophore, and sometimes fluorescent dyes, labeling ribbons or strains. So looks like a full, so, I mean, like we are seeing the fluorescent day to day life. Like if we can see the leaf, like it looks green, but it's basically when the light falls on it, it absorbs the every wavelength except the green, and it reflects back the green. So we can see. So basically, we just see only a green light. And again, for example, apple. Like we can see, apple is red. It's not actually a red. So like apple, when the light falls on it, it absorbs the every wavelength except the red. So and it reflect back the red. So and that's why we can see that apple is red. A fluorophore, like like fluorophore means absorb light at lower wavelength, that is excitation, and emits light at a longer wavelength. So basically, if we like a fluorophore means like it absorbs energy of lower wavelength with a higher energy level, and but it emits a lower energy with a higher wavelength. So next is working principle of fluorescence. So, when the photon hits on the on electron, the electrons will move from ground state to higher state. So, because of unstable condition, it comes to some metastable condition. And when it comes from unstable condition to metastable condition, the loss that is actually get converted into a thermal energy or a vibrational energy. So it is actually a non-radiative uh, radiation. So from metastable condition, it comes to a ground state. So the energy that it has absorbed and the energy with which it is coming down to the ground state have a different wavelength and different energy. That's why if we are if it has absorbed a wavelength of some green light and it is now emitting a wavelength of some red light, so this is what is happens in the fluorescence, and uh, it that the electron at metastable condition, it goes to the intersystem crossing also, where again it again come to some again a metastable condition. And from this again it comes to come to a ground state with a different wavelength. So this is basically absorbing with a different wavelength and emitting and coming back to the ground state with a different wavelength. So this is what is happening in the fluorescence, and we can calculate what is the wavelength by using this formula. We just need to we just need to know what is the energy difference between these two and these two and these two. So timing of fluorescence. So this process actually takes some time. It's basically in a micro or milli or microsecond or nanosecond, but it is too fast. So basically, from ground state to the excited state, it will have some. It will take some 10 power minus 15 seconds, which is actually very fast. And from unstable condition to it will come to a metastable condition, and again from metastable condition it will go to the excited temperature, where it will take around 10 power minus 10 to 10 power minus 8 seconds. Again, the electron at metastable condition, they will come back to the ground state. It will take again some times, which is actually fluorescence. It will again take some time, and and this element also comes back to the ground state, and it also takes some 10 power minus 3 to 1000 seconds. So this is basically this is the fluorescence, and this is the phosphorescence. Fluorescence is in generally very fast. So it is in nanosecond decay time. Sometimes special fluorophores have longer decay times, like in macro and millisecond decay time. This can be used to improve the signal to noise ratio. Next is coherent and incoherent optical amplifier. Coherent optical amplifier is a device that increases the amplitude of an optical field while maintaining its phase. So basically, where we see this coherent amplifier and coherent like laser. Laser is actually a coherent coherent ray, which is actually a directional, and it has the same phase with same amplitude. If the optical field at the input to such an amplifier is a monochromatic, the output will also be a monochromatic with the same frequency. The output amplitude is increased relative to the input while the phase remains unchanged or is shifted by a fixed amount. Incoherent optical amplifier, basically LED scatters in every direction, and it is the incoherent rays. Incoherent optical amplifier increase the intensity of optical wave without perceiving its phase. So this is actually what we have seen. This is actually what we have seen the stimulated emission where the photon of the same energy of this energy hits, like it will emit two photons with the same characteristic. So this is what happens in the laser also. For laser to happen, the the atom has to be at the some excited states. So like this, when again when a photon hits, the electron move to the excited state, and again it decays to the uh, ground and it forms the laser. So for this, the electron has there are so many electrons that has to be in the excited state. Laser. Laser is an acronym for light amplification by stimulated emission. A stimulated emission allows the photons in a given mode to induce an atom whose electron is an upper energy level to undergo a transition to a lower energy level, and in the process to emit a clone photon into the same mode of the initial condition. So this is what is happening. So the atoms whose electrons in upper energy levels to undergo transition to, so for this for this to happen, there should be a electron at upper energy level, and then only we will have so many of lasers. So basically here it is 694.3 nanometers of wavelength, which have the same phase and same characteristics. A clone photon has the same frequency, and wavelength, direction, and polarization as the initial photon. These two photons in turn serve to simulate the emission of two additional photons and so on. While preserving these properties, the result is coherent light amplification. Because stimulated emission occurs only when the photon energy is nearly equal to the atomic transition energy difference. The process is restricted to a band of frequency determined by the atomic line width. The next is a metal semiconductor insulator. Metal is conduction. So what does metal mean? So it has a conduction band which is close to a valence band. The electrons are easily excited out of the valence band. Electrons in conduction band are free to move. So this is basically a conduction band where the valence band and the conduction band is actually there is no gap between them, and the electron can easily move from here to here. Next is a semiconductor. Conduction band is relatively close to valence band. Electron can be excited out of the valence band under certain condition. So this condition, this is the a semiconductor where there is a difference between there is a gap, energy gap between valence band and the conduction band, which is generally equal to 1 electron volt. Insulator. uh, in conduction band is far from a valence band. Electrons not easily excited out of the valence band. In semiconductor, the electron can jump from this to conduction band, where in insulator the energy gap is too much. Like the energy, the like it if it is more than 5 electron volt, the electron can't jump from um, valence band to conduction band. So in daily to daily life, in electronic gadgets, generally this is not conductor is also not useful. Insulator is also not useful. Basically, we use the semiconductor, and it is actually highly demanded in the industry. Next is four-level pumping. Four-level and three-level pumping schemes are used in practice to achieve a population inversion. So basically, population inversion means like we have seen, I was discussing about the electron in the in the higher level has to be more than the electron in the lower level. So this is basically called the population inversion. The object of this arrangement is to make use of an excitation process that increases the number of electrons in an atom populated in level 2 while decreasing the number populated in level 1. In this arrangement that is shown in the figure, level 1 lies above the ground state. So this is actually a level 1 and this is the ground state. In the thermal equilibrium, level 1 will be virtually unpopulated. So this is actually unpopulated. So pumping is accomplished by making use of the energy level that lies above level 2. We designated this level as level 3. The 3 to 2 transition has a short lifetime, so that there's a little population accumulation in level 3. Level 2 is long lived, so that it accumulates the population, whereas level 1 is short lived, so that it shares population. A population inversion is thereby established between level 2 and level 1. Four energy levels are involved in this process. So this is basically four levels, but the optical interaction of interest takes place between level 2 and level 1. So basically here what is like here we will see the population inversion. So like what happens in this, like when we pump when we like incident of photon, so the electron from ground state will excited to a higher state. So because of unstable condition, it will rapidly decay to some metastable condition. So like for the and it will stay here for a line for a little bit long, and then again from metastable condition, it will come to a some like the electrons here will be much greater than the electrons compared to this one. So again, it will come back to again some again another metastable condition to level 1, so, which emits a laser, like which emits the photons again, and uh, from this metastable condition, it will again come to a ground state. So basically, we will see population inversion between level 2 and level 1, because from when we pump the when we incident of photon, it will go to metastable unstable condition. From here, we will have so many electrons at metastable condition. Three-level pumping. A three-level pumping arrangement, in contrast, makes use of ground state as the lower laser level 1. The third level is involved, and the 3 to 2 decay is rapid, so there is no build-up of the population in level 3. The 3 to 1 decay is slow, so that the pumping serves to populated level 2, the upper laser level. So here we are seeing in the previous, like it was a 4 level. Here it will be only a 3 level, where when the incident of a photon, the electron at ground state will come to a excited state, and from here it will go to a metastable condition, and we will have a population inversion over here, because there are the number of electrons at higher energy at this level will be more than the electron at ground state. So we will see the population inversion, and it will help for the it will to make a laser. And an electron in an atom are pumped from level 1 to level 3 at a rate R. Uh, Fast decay effectively pumps level 2 at the rate R2, which is equal to R. The thermal excitation for population of level 2 is assumed to be a negligible. LED, light emitting diode. An LED is just like a normal p-n junction diode, but with light emitting properties. Like an ordinary diode, the LED diode works when it is forward biased. In this case, the n-type semiconductor is heavily doped than the p-type, forming the p-n junction. When it is forward biased, the potential barrier gets reduced, and the electrons and hole combines at the depletion layer. Light or photon are emitted or radiated in all directions. How to get the different colors in LED? Basically, dopant atoms are added to gallium arsenide to give out a wide range of colors. Some of the materials used in LED are aluminum gallium arsenide, which will give the infrared, which we can't see by our naked eye. Then gallium arsenic phosphide, which gives red, orange, and yellow. Then we have aluminum gallium phosphide, which gives green color. Then indium gallium nitride, which will give blue green, yeah, and near UV. And then we have zinc selenide, which will give blue color. Next is nonlinear optics. In that, let's discuss about the fundamental view of nonlinear optics. So basically, nonlinear optics is actually like whatever we are seeing, like absorption, emission, spontaneous emission, and stimulated emission. Those are uh, uh, those are all nonlinear optics. So linear optics is basically like we have absorption and an emission with the same energy. There is a microscopic view adopted to discuss the light matter interaction with interaction process that the oscillating electromagnetic field lead to electronic polarization of the charged particle. This is the polarization equation, and this factor, this one, two, and three, will actually define the harmonic generating in the process in the photon. So if it is one, then we will have a simple linear optics. Like there will be absorption of the same energy, and there will be a the atom will come down through ground state with the same energy. If it is two, then we will have a second harmonic generation. Like for example, from ground it will at some energy level it will go, and again from that it will go to the excited state, and then from excited state it will again come back to ground with a wavelength with a frequency of omega 2, and like the both this is omega 1 and omega 2 will have a different light and different wavelength. If it is three then it has a third harmonic generation. Then it will have three steps in between excitation state and the ground set. And again, the omega 1 and omega 3 will have the different wavelength, and the color will also be different for this. So this is the linear optics, and this is the non-linear optics. So thank you. This is all about the introduction to photonics. So thank you once again.